Previous time, Shamil was talking about quantum Dell system and the Hamiltonians which he obtained for it. And today, in some sense, I will continue his talk. I will consider some degeneration of this double elliptic integrable system, which will be trigonometric in coordinates, however, still elliptic in momentum. Previous time, Shamil said about it that it's also some kind of new system. He said, however, that should not be called dual elliptic Regener system. But as I forgot to ask him why, I sometimes will call it like that. And the purpose of this talk is to construct infinite number of particles limit for the system. And that's our main goal. The talk is based on our joint work with Andrei Zotov.
Andrei, just for expectation of what this kind of limit can be, can you say what is the, for example, infinite particle limit for Calogero motors for some simpler systems? What that would be infinite particles limit for Calogero motor or Regener Schneider?
Well, yeah, they are described, but well, I don't know how it's called. It's some kind of for Calogero, it's some kind of even field theory, we could say. I forgot what it's called, Benjamin Ona or something like that. I couldn't, I don't remember its name exactly.
So we should expect again some field system, not the particle system.
Yeah, yeah, of course, yeah, sure. I mean, I will describe in the talk what exactly is meant, what exactly I mean by infinite number of particle limits. But of course, I mean that our Hamiltonians will act on the space lambda of symmetric function, which is inverse limit of spaces lambda n of finite number of particles, and so they will be expressed in terms of power sum symmetric variables and their the conjugate, yes, the derivatives in terms of them. However, for this case, it will not be like field theory system. It will be extremely non-local, of course. So, in contrast with the usual Calogero, where we could say that it, in some sense, it sounds like field theory. Here, we will only give expressions in terms of the modes of the field, Pm, right? Power sum symmetric function, and but it will not make like a lot of sense as a field theory. I'm most interested because in that because of the connection to representation theory. Okay, I'm not sure that answered your question properly.
Yes. Okay. Go ahead, please.
Okay, so I'll here is the plan approximately. Here with pluses, I marked the points which will be discussed today, and minuses, the points which I will not discuss, but they also were done in this works, and some of them I'll need today. I will use. So at first, I'll remind you what actually how the Hamiltonians looks like, starting from Calogero motors and Regenars as usual. And then I will proceed to main part, which is at first construct the analog or the analogs of Cherednik operators for the system for this trigonometric degeneration of Dell. And then I'll proceed to infinite number of particles limit. At first, I'll review what does it mean in general, and then I'll show how to apply these general ideas in our case using the so-called Nazarov Sklyanin construction. Well, this work is actually a step-by-step generalization of the results for Regenars. It's actually the same. And in the end, I will briefly comment on the relation of these Hamiltonians to representation theory of elliptic quantum toroidal algebra, which was described recently in the paper of Mironov, Morozov, and Igor Zankevich. Okay, so actually the things which I will not describe here, but I will use it as a theorem, is the eigenvalues for this system. it was like it was obtained using this huge DBR-McDonald determinant. This is like a separate part of the talk. I will just use it, but not proof. Yeah, and also some organizational comment. With all the proofs, the talk will be like 1 hour, 10 minutes long. But as usual, I think as we go slower, some proofs I will not give immediately, but in the end, if someone asks a question how to prove that with this statement, I will return to them. I think it will be better like that. Okay. So let's go first to the first part, to model system. The first non-trivial Hamiltonian fluid looks like that. Qi is just position of particles and the number of particles. And the system is integrable. It's only the first Hamiltonian in the series of commuting operators. I will not write down the rest of them explicitly because I will not need the expressions for them. And it's well known that it has also trigonometric and elliptic generalizations. And but it's not the end of the story. We also have trigonometric and momentum generalizations like Ruginar's system or Ruginar's system. I forgot how to pronounce his name, which look like that. And for them, I think it's already will be convenient for us to write down the higher Hamiltonians because they'll be already closely related to Dell integrable system. The expression for them, they look like that. Just sum of subsets of indices 1 to n of such products, and they could be recast into the generating function, which is more convenient to work with because here the sum is of all subsets without restriction. And also they also commute with each other. Okay, so from here, it's already maybe sounds natural that if we have system rational trigonometric and elliptic coordinates, we might expect that there should and system which are rational trigonometric and momentum, we might expect that there exists system elliptic and momentum. And it was conjectured like many years ago. It was discovered on classical level and studied a lot. And recently, the quantum generalization was given by Shakirov-Koroteev Hamiltonians. Well, I will not mention all the story again. I think Shamil already described it a lot. Talked a lot about history. But today we will mostly will concentrate. Our attention will be concentrated on this box to the left from Dell system, which is.
Sorry, Andrei, but Shamil said explicitly that his Hamiltonians, their Hamiltonians with Koroteev, has nothing in common with this table.
I mean with the previous one.
With this table you show now.
Well, no. Well, why? I mean.
Well, just because he said they checked that. Well, this is in elliptic case. It has no self-duality in this sense.
Yeah. Okay. You're right. Maybe maybe I should not use the table, but I mean the flavor of the statement is still the same. I mean.
Yeah, but it's a question to you. So, in what sense as I understand, you will speak about this middle low rectangle, yeah, which is called dual elliptic Rusinars.
Well, yeah, but
is it really dual to elliptic Rusinars in the Rusinars sense?
No, probably no.
Well, so just the whole this slide is misleading, and it's better to remove it.
No, because otherwise, how will introduce Dell system at all? Well, okay.
Well, I don't understand. So there are many ways. So one of the way is how it was. Well, we tried to do long ago, like in this right lower corner, and maybe there are some other things. But Shamil told us that Koroteev and Shakirov, they did something different. And,
well, yes,
and also reasonable. So it's an issue how to introduce it. It's not, why do you say how?
Well, okay, I use it
there are
like
probably many ways, and you should state your own way, or but not give any misleading arguments then.
Well, okay, I agree. Well, I will use Shakirov-Koroteev Hamiltonians just as a definition. I mean, it's not clear right now how to make them self-dual or to relate to this dual elliptic Regener system, but they actually should be related because we know from field theory arguments that they're correct, because the solution is six-dimensional partition function with defects, with orbifold. So they should be the same in some sense.
Sorry, but when you say about self-duality, what self-duality do you mean? When action coordinates exchange with momentums, or what?
Yes, in coordinates exchange with eigenvalues of Lex operator. It's on classical level.
Okay.
And well, but the best is just to write down this equation and this elliptic case, if you can do this. And
yeah, we'll do it right now. I mean, well, I decided to add the slide as the kind of motivation. Yeah, but probably maybe I should skip all the beginning because it's also already described by Shamil and much better. Yeah. So, but still, I would like to start with some motivation. At least the comparison between these Hamiltonians and Regener Hamiltonians. We see that the Regener Hamiltonians could be expressed in such equivalent form, just sum over numbers which take values in set 0, 1. And this is equivalent to previous expression. The subset I is just those of n i's which are equal to 1 here. Yeah, and Shakirov-Koroteev generating function is generalization of this expression with elliptic measure here. However, in the elliptic case, they do not generate the Hamiltonians, but the Hamiltonians are generated by the ratios of these modes. Okay, so right now we reach the moment where Shamil stopped previous time. Yeah. Yeah, and to answer Andrei Marshakov's questions, I will use this as a definition. I mean, the whole discussion will start from this point.
so again, there is nothing like relation between Lux matrix and matrix of coordinates, or it exists.
I don't know. No, I haven't tried this. Haven't tried this for the system. Well, I mean,
well, by the answer, and at least it looked so from the talk of Shamil that there is no such relation for these particular Hamiltonians. And but you just take these Hamiltonians and then take the generation of theta functions. Yes.
Right. Yes, exactly.
Okay.
That's what I'll do. Okay.
Was the question about group theoretical meaning of that Lux operator?
But there wasn't even Lex operator yet. I mean, the question was, in principle, as we obtain this Lex operator, we might try to check whether how Q duality acts on it, and whether it'll be self-dual or it'll be mapped to something else.
Oh,
Probably
I see.
it will be mapped to something else, as it was mentioned by Shamil. Right? We may try to see what it is. So it's not like complete unsolvable problem, but just I haven't checked this.
Okay.
Okay, so now I'm finished with introduction. Now I'll go to the Cherednik construction. First, I revise it in the Regener's case, how it worked. As we know, to introduce Cherednik operators, we need to go to the larger space, not just symmetric functions, but polynomials. Okay. No. However, it's more convenient for us to work with. I need to change notations first. I'll go to multiplicative notations, which Shamil has previous time. So instead of introducing, instead of writing particles qi and the moment, I will go to exponents like he did. And there's then the expression for the Wisnar's genetic function look like that. Okay, so now I'll introduce this bigger space of polynomials, C x1, xn, and how the permutations operator, how the Cherednik operators act on them, how to construct them. The first operator, we need to introduce a permutation of variable. We just change xy coordinate to xg. From them, we could construct the R matrices acting on this space. And from them, we could already build the Cherednik operators. They look like that. And the theorem is at first that these operators commute on the space of polynomials C of x1, xn. And second, that being restricted to space of symmetric functions, lambda n, the symmetric powers will give the Hamiltonians of Ruzhina-Schneider model. That's how it worked in usual Ruzhina setup. Now we'll try to do the same for double elliptic systems or for, in our case, trigonometric degeneration. But to do this, I need to introduce a new notation. It is as follows. For any operator A, depending on Q and T, its square sum, like A to the power n, will be the same operator, just with Q and T replaced by Q to the power n, T to the power n. And some kind of average with operator with elliptic measure will be denoted like that. I don't know how to call this operator properly. I denote him as p theta function, but it's actually doesn't have any properties of theta function because it's linear. It's linear.
For Q and T.
Q and T are this where our exponentiated coupling constant and
So, but they are at least they're numbers. Yeah, they're not operators.
Yeah, Q and T are like numbers. Yeah, it's like a coupling constant and Planck's constant. Yeah.
No, they are not numbers. If you find, if you say that there are 2 and 3, for example, you cannot find 2 and 3 and replace with 2 to the power n and 3 to the power n.
Well, but they are number constants, whatever. But just to distinguish between gammas, for example, and q's. Yeah, so you will take the powers only of Q and T, not of the operators.
Yeah, right. I mean, it's just like, for example, let's look at any example. Yeah, for example, for this operator, it depends on x's, yes, but it actually also depends on Q and T. And taking its n square power means just replacing T inside and Q is inside by power n, by T to the power n, Q to the power n.
So is it correct that at this moment you do not touch this shift operator?
Well, it will touch it through Q. Yeah, I mean, it will touch it, right? Because shift operator is Q to the power xg times derivative. So when we replace Q by Q to the power n, the shift operator will be replaced by gamma to the power n. You mean this? Well, I don't know. Maybe my notation is not clear. Well, okay, but I'll consider one example very soon. As soon as it stands the theorem, I will consider 2 by 2 example. You will see how this operation works. Okay, so also I changed the notation for the elliptic generating function in the same way as I did for Ruzhina's first. And for it, we could already formulate the theorem.
I'm sorry, what's omega? Is it an additional parameter?
No. Omega is the same. It's a parameter of elliptic deformation of our system, right? Okay, yeah, it's the parameter which we have in Shamil's Hamiltonians. Yeah, we had the two elliptic parameters, one for coordinates, one for momenta. The one for coordinates we just killed. Yeah, we send it to 0. We're left with one which is for momentum.
Right, thank you.
As you can see, yeah, omega stands here in front of everything, yeah, in the measure, and just measures how many, how much elliptic in momentum we go. Yeah, and it enters this definition of theta function, p theta function. So here, actually, we lost part of the theorem. Now these operators do not commute with each other. So we need to take care about the order here, but the statement still remain true. The generating function.
But have you defined this C1, Cn before?
Yes. There were usual Cherednik operators.
Usual Cherednik operators. I see.
So we just need to apply this complicated operation to them, take the sum of all the Cherednik operators with different Q and Tn, and then take such product. I decided to show how it works in 2x2 case. In principle, we could spend some time just looking at this next 3 slides where I just did the calculation for 2x2 case. So look, that's how this operation worked. I applied it to the first Cherednik operator. It has only one error matrix and one shift. So you see, I just changed all T's and Q's by T to the power n, Q to the power n. And this also, as Pasha asked me, this also will change the shift operator because it has Q inside. And the same for second Cherednik operator. In 2x2 case, it also will be just shift times the inverse of this error matrix. And I also did the same to it. Well, I know that these formulas are hard to follow on slides. So I want to give some additional time for everyone to look at them. Then I'll just multiply. We'll get sum of the two integers. And after that, we need to restrict to a space of symmetric functions. The first error matrix is restricted trivially because here we just replace sigma 1, 2 by 1, and this sum becomes identity. And the second one, we need to treat more carefully. Yeah, it will change the order of shift operators here. So we'll get two terms with different orders of shift operators. And then gathering the terms in terms of the fixed powers, we obtain this expression. In principle, I could do this calculation later, I think, on this Zoom Blackboard. If it's not, it's hard to follow like that.
Well, what maybe you can just now say about the result, it gives you this generating function, but the ratio of coefficients give Hamiltonians, yeah?
Right.
In this case, not the terms themselves.
Yes, that's why we don't even expect that these Cherednik operators commute, because we know that restricted to the space of symmetric functions, they definitely already not commute. We need to take ratios. However, more non-trivial question might be, what if we try to take the ratios of these Cherednik operators here? Maybe then they will commute, because we know that restricted on space of symmetric functions, they commute. And Andrei Grekov checked this numerically, and they still don't quite commute, but commute on some complicated powers, some strange number of monomials. and it's not really clear right now what is the correct way to change the separators so they become commuting, or how to, and why they commute on some powers still? Is it like a miracle or what? But right now we don't have any commuting version of Cherednik operators for the Dell system.
And is it clear from the beginning that this operator will act from a symmetric space to itself?
Dn. Well, it is a good question. I mean, it could be done. It could be checked exactly in the same way as it was done for usual Rusinar's operator. Yes, they will preserve. It's like, for example, using the Siriguchi-Debert-MacDonald operator, it will become quite easy because you will express it as a ratio of some determinant and van der Monde determinant. And then it will be easy to see that this determinant is antisymmetric, and as van der Monde determinant is also antisymmetric, everything will be cancelled, and symmetric polynomial will map to symmetric polynomial. Yeah.
Did you just explain how to check this once we computed the general formula for this DN, or it is clear also from this construction with Cherednik operators?
From Cherednik operators? No, I'm not sure it's clear. No. You mean? Wait. You mean follows trivially? That you already restrict them? Well, I haven't thought about it.
No, I don't know. I didn't say it trivial.
No, I haven't thought that the fact that we express them in such a way means that they preserve it. No, I mean, I think it's better. I think it's easier even to check it just directly. I mean, like it's done for Rusinars. I mean, the proof is not changed anyhow. I mean, almost not changed anyhow. Well, of course, it will be interesting to find commuting Cherednik operators. And yeah, you may ask why I even say this is Cherednik construction. It might be some complete nonsense, right? Just find some operators. Why they even make sense at all if they don't commute? But actually, they will be needed to construct infinite number of particle limit. They're useful for this construction. Apart from them, they might be not useful at all. Yeah. Okay, I also actually have a sketch of the proof of the Cherednik theorem, but I think I'll skip it and then maybe return to it if someone asks how to prove. Okay, so now we could move on to the second part of the main part of the talk, the main body of the talk, which is infinite number of particle construction. So the idea, at first I'll describe the general idea. What does it mean to construct infinite number of particle limit for some Hamiltonians? Consider such homomorphism from lambda n to lambda n minus 1. We just send the last coordinate to 0, the last coordinate of each polynomial to 0. And we could consider the inverse limit with respect to this maps. And if we have some Hamiltonians acting on the space lambda n, some Hamiltonians Hn, for each n, we could ask, could we construct some operator Hu acting on this inverse limit such that it preserves this projection from the inverse limit. Yeah, it's like general general formulation.
When you say Hamiltonians, is it the only property to be satisfied by H of U?
Well, I should also commute. Well, I think it would be automatic. Well, yes, I think yes.
Commute at different values of U or what?
Yes, right. The HU, yeah, by HU I mean not the generated function of Hamiltonians. Yeah, HU is like if we expand it, we get Hamiltonians. This is what I mean. And Pn is the standard projection. Yeah, as you know, this space lambda has a basis Pn power some symmetric function. Pn just sends them to power sums, to actual Newton polynomials.
Andrei, but your D of U is not a Hamiltonian.
Yes, right. D of U is not, right. That's why I write it H of U here, because it's some H which will generate Hamiltonians. I just haven't specified yet what H I mean here.
Okay, thank you.
It will be described later, right? Yeah, it's a nice comment. Yeah, maybe I made some confusing slides. Yeah.
Sorry, Andrei, probably I missed. Are operators Cherednik satisfy Young-Baxter equation? Yes.
Cherednik operators.
Yes,
No.
R.
Yes, they should satisfy.
Okay.
But of course, yeah, and that's why, because that's why CIs commute. It's one of the reasons. However, as soon as you take this p theta function, it will be lost. All this property will be lost because you will encounter R matrices with different coupling constants there, and there is no Young-Baxter relation between them. There is no if you have one R matrix with parameter t and one is t square, yeah, they will not satisfy Young-Baxter equation like if they have the same t inside. It will not work.
Thank you.
Okay, so here the problem is the following. Even for Rosinar's system, we know that Macdonald polynomials are stable under this limit, so I will not even write any additional index n for Macdonald polynomials. I always denote them m lambda, even for any n and for inverse limits also. However, the Rosinard separators are already not stable under this limit. They do not commute with the homomorphism, projection homomorphism. It could be seen from the expression for the eigenvalues. If we act by the generating function of Macdonald polynomials, it will give us some eigenvalue expressed in terms of the Young diagram. And if we act on the opposite, in the opposite order, it will give us the same expression except for the last term. So they will differ by such a bracket, such an expression. But this could be easily fixed in principle. You just need to divide the generating function by such product. So to compensate for this factor here. I don't know who did it first. Who was this idea? Probably something easy, but I read it in the paper of Nazarov and Sklyanin and decided to mention it here because they actually construct the inverse limit for the Rosinard-Schneider operators in such way in this paper. They called AFU. It's now well defined, and they give some expressions for it in terms of standard symmetric functions. Yeah, that's one of the way to solve this problem. However, it's not the one which we will use. We will use slightly different approach. The second approach, how to deal with n to infinity limit of Hamiltonians, is the following. We need to consider the ratio of two Hamiltonians, generating function means u of t and u, with arguments u of t and u. By itself, it will not cure anything, because we'll still have the same problem. Just now we'll have the ratios of these two factors here. It's still not a solution yet. However, we need, so we couldn't still find a preimage of en, in inside of lambda, acting on lambda. But we could use some trick. We could do something else. We could enlarge our space lambda with one additional variable, one formal variable which we'll call w, and extend our standard projection Pn to this to the space lambda w, which will actually play the role of auxiliary space for our system. And the extension is self-explanatory. It just says this formal variable w to t to the power n, and then these two factors here will be exactly the ratios of the images of the same expressions in terms of w, just for different projections. This will be projection Tn, this Tn minus 1. So we could construct the inverse limit, but for other space, for enlarged space and for extended projection.
Sorry, I didn't follow this. Like your operator. You have like, okay. You have added w to your operator.
Yeah, we have added w to our space. Where we want our operator to act, right? So
yeah, but does the operator depend on w?
Yes, right here. So the operator will depend on w, and I even write down the explicit form how it depends. This one downstairs. The w enters the expression in such a way that it will compensate this factor here, u to the power t to the power n. So now this operator makes lambda to space lambda w, but however, it agrees with the projection. It agrees with the projection tau n. So the price we paid for this agreement is that now our space is bigger, and we have additional variable, and our operator actually maps space of symmetric function to something else.
I'm sorry, what is the difference between this approach and what was in Nazarov Sklyanin paper? I thought that there you also had explicit dependence on n. There was some product to n minus 1, right?
Well, okay.
So why not?
Yes, that's very similar. Yeah, right. Maybe Pasha is right. It's just a different way to say it. Yeah, maybe just a different point of view. There we just divide Hamiltonians by this product and construct the limit inside of lambda. Lambda. Here we construct the inverse limit inside lambda w. But however, the dependence on w is quite easy, and it could be eliminated by hands. Yeah, right. That's probably what Pasha is saying, that we could now divide just by 1 minus uw and call this expression the new limit. It's just by definition, we'll call this expression curly I the new inverse limit. Yeah, but the difference is still that we introduce a ratio. That's what I mean, the difference, that we work with the ratios now.
Also because otherwise they do not commute, right?
Yeah, that's also wanted to comment. In Reznar's case, it wasn't needed. I don't know why Nazarov and Sklyanin decided to consider the ratios of Hamiltonians. It was like not natural at all. And they did it even after they construct the inverse limit for usual Hamiltonians without ratio, which this AU, which I mentioned. So I don't know what was their motivation, but in some sense, the construction is so genius that for Dell it worked because for Dell the second option works and this first do not, because in first case, I mean, they're not commuting Hamiltonians, right? In principle, they still might have some inverse limit, but still not commute. So from the point of view of Dell, it was natural to consider this ratio, because this ratio is a commuting operator, generate commuting Hamiltonians. For reasons I don't know why they decided, but it was very, it's very good that they considered it, and now we could generalize it for the system without any problems, because now the ratio still commute. Yes, yeah, also very good comment, yeah. Okay, so now we need to do the same for dual elliptic Ruginars, okay, or coordinate trigonometric degeneration of Dell. I recall the expression for the generating function and the theorem which we need to use. Like I mentioned in the beginning, we need to use the expression for the eigenvalues, which need to be derived separately. But as soon as you know it, you could repeat everything in exactly the same way. The difference is like only in the following. Now dn tu doesn't commute with dn of u, so we need to specify how we take the ratio. And actually we take it from the right. But the rest could be repeated in the same way. Just everywhere we'll have elliptic function instead of products, instead of rational functions. We still construct these operators en, their inverse limit in the space of lambda w with additional parameter, and then get rid of the dependence.
And who are m lambda of w?
Some,
m lambda of omega.
it's some eigenfunctions of these operators, which are some deformations of Magloan polynomials. In principle,
do you know them?
Yes, I mean, in principle, they are known explicitly. It's still a conjecture, but Samir actually talked about it in previous time, and the answer is the following: you just take the usual Magloan polynomial. It will be some expression in x1, xn, with coefficients being some rational functions on q and t, which will always have the form like 1 minus q to some power, t to some power. And then you just changed this rational function to elliptic function with parameter omega. And this will be this deformation. But I will not need it in the talk. I will not need the explicit expression for the wave functions. So I just call them some letter m lambda with parameter omega, like deformation of Magloan polynomials. Yeah, but also things that you ask, in principle, this wasn't explained on the slide here. Okay, so that's the idea of the construction. And now I am planning to present the answer. And in the end, I'll try to explain how it's derived. But I thought it's better to give the answer first and then explain it. Then just start deriving it. I thought it'd be less confusing. So I'll do it in two steps. At first, I'll explain the structure of the answer, and then I introduced all the notations needed for it. So the structure of this final operator curly I, which is already where we mod out all this W dependence, will be the following. It is a sum of integers, two pairs of integers, and two subsets inside of integers with some coefficients which depends on u, omega, and q and t also of such products, where all the separator pi, LEG, and beta are defined below. we have our auxiliary space lambda v, which is actually the same as lambda w. I just introduced for convenience one more formal variable because it's just easier to express some operators as operators mapping lambda v to lambda w as instead of just lambda v to lambda v for convenience. And then from the point of view of this auxiliary space, beta is a column vector. No, beta is a column vector and y is a row vector. And alpha and x will be like matrices acting on lambda v, like infinite dimensional matrices. So what we have here is the following. We construct some infinite number of L operators from y and x, take some products of them, and after that, using y and beta, we take some matrix elements in this auxiliary space. So this sum here is actually sum of matrix elements of infinite number of these L operators. So that's the structure.
And yeah, what is here the meaning of brackets on these integers?
Yeah, brackets is exactly as in the beginning of the talk. It means that y, beta, and alpha, x, they all depend on q and t somehow, the sum operators. And we need to raise q and t inside to the power n when we write y to the power n.
Mm-hmm.
Okay, so to give you the complete answer now, I need to specify what alpha, beta, x, and y are, and also how E I just expressed in terms of them somehow universally. I'll do it step by step. I'll start with definitions of alpha. It's natural to expect that alpha, as all the operators, somehow expressed in terms of symmetric functions. Yes, or operators acting on space of lambda somehow with some as coefficients with something acting on space of V. Namely, they will have the following structure. They all will actually be expressed in terms of the generating function of whole Littlewood polynomials. QV is exactly the generating function of whole Littlewood polynomials, and Q star is its conjugate with respect to Macdonald's scalar product. So it replaces.
Sorry. You told that W was a kind of t to the power n, and then that V is the same as W. So is it the same here or not?
No, actually it will work like follows. For V, we will never evaluate it. For V, we will just will act like that. Beta will create the powers of V, as you can see, and then we'll apply operators x and alpha somehow on this space, and then y just will kill it. So we'll not need to relate it to t to the power n. I mean, inside the Hamiltonians, V will not appear. It will be just killed by y. It will be it will be actually sent to W, and then W will be evaluated like that. But I will show. Maybe I'll show how this will work. Yes, it will be some operator which sends lambda V to lambda W, killing powers of V somehow and creating powers of W, and then W will be eliminated by this trick which I tried to explain above. It will be like that.
So, and should this be understood as a kind of coordinate of some extra particle or not?
Yeah, that's also a good comment. I'll even answer your question in more details later. In some sense, we have some natural projection also from lambda V to the space to the space of polynomials symmetric in all variables except for, say, first, right? It will be like that. So I'll explain it in the construction when I start deriving it. Yes, that's true. It's in the construction of inverse limit, we'll have some operators which preserve not all lambda n, but actually the space of lambda, the bigger space, symmetric in all variables except for the first. And this v will consider natural projector which will send v to this first variable. Yes. So your question is correct. Yeah. And what you're saying is right. But it will be like auxiliary step inside the construction, right? Okay, so now we'll back to definitions of alpha, beta, and x and y. I'll just write them down as four matrices given explicitly on powers of v. It's like a basis in the space of lambda v for v. So I mean, by this I mean that it still could act on some symmetric function, and the action will be given by this q here, q and q star. But yeah, these questions actually probably don't explain anything. I just try to formulate the answer in the most straightforward way. But at least you could see that beta is a column vector and y is a row vector, because beta in some sense creates v out of nothing and y kills v. Now the last step, I'll need to write down how curly I operator depends on all this x, y, alpha, and beta. And this will be some ugly expression. I just, before writing, I want to, I don't know, to warn you that it's ugly. So it's some inverse of some infinite sums of these operators alpha, beta, x, and y. So because it's so ugly and not eliminating, I decided to expand it and show you several first few terms in this expansion to just at least explain how it works.
And this is like quasi-determinant of some 2 by 2 metric in the denominator, yes? No, something plus quasi-determinant.
Well, I don't know what is quasi-determinant, but yes, this thing actually appeared from, yes, right. This expression appeared from the from inverting some 2 by 2 matrices. So yes, right, and probably what you called quasi-determinant is what is some kind of non-commutative analog of the determinant. Yeah, what? Yes,
yes.
Right. This expression arise like that. It was some 2 by 2 matrices. We tried to invert it and get this determinant, right? It will be mentioned a bit in the end. How these 2 by 2 matrices appear.
This is answer for the case n equal to. Oh, sorry, yes.
No. It's a general answer.
Yeah.
I mean, it's not n equal to.
But how 2 by 2 matrix appeared?
Yeah, I will explain at the end. Yeah, it's not 2 by 2 matrix actually appeared like that. We will have space lambda v could be decomposed into lambda plus v times lambda v, and it's not. It will be some 2 by 2 matrix in this some decomposition of operators into this with respect to this expansion. Yeah, lambda plus v lambda v. But I'll tell it in the end. Yeah, we will get to it probably. But at first, I would like to show how at least first 2 non-trivial terms of first 2 non-trivial Hamiltonians look like. The I0 is probably not completely non-trivial. It's because its limit is omega goes to 0 is actually trivial Hamiltonian. So I don't know exactly. Maybe this is already will be some not independent Hamiltonian, so I don't know. But I1 is definitely non-trivial because it starts with it starts with Ruzhinar's Hamiltonians. Here, G0, G1, and so on are Ruzhinar's Hamiltonians. I mean, inverse limit for them. And K1, K0, K-1 are some expansions which arise already to the first order in omega, which are not expressed in terms of Ruzhinar's Hamiltonians, which is something else. Probably this expression also doesn't explain anything except for the limit omega goes to 0. I also have explicit expressions for k's in terms of y, alpha, and x. So as I promised, beta always stands from the right, y always stands from the left, and in the middle we have L matrices. And if you write down them explicitly, they will look very ugly. So here also, I don't know, I'm kind of embarrassed to present it, right? But I haven't come up with more clear structure of the answer. So the best general expression is this. However, if you would like to use it, you need to expand all those p theta functions and then expand the inverse and get all those ugly expressions, which do not reveal anything. I think.
So, Andrei, sorry, but some general questions. So you're saying ugly, but have you expected something good in this n to infinity limit?
Yeah.
Why did you expect anything good, or?
Yeah, I'll explain. Okay, it's a good question. So my only motivation to do this was actually to relate everything to the representation theory of some algebras. And as you know, if you take for example, look at the expression for G0, it's a Ruzhinar's Hamiltonian, first Ruzhinar's Hamiltonian. For Ruzhinar's, it's known. It is known that all the Hamiltonians are actually some residues of operators acting in quantum toroidal algebra. For example, here you see it's the residue of QZ times Q star Q inverse Z, such a vertex operator. This is exactly, if you remember the expressions for Q and Q star, maybe already not, this will be exactly Drinfeld current in quantum toroidal algebra. So I was hoping that maybe it will not be restricted only to G0, this magic, but it also continued all this K1, K-1, and so on, and I'll be finding some nice way to describe them in terms of some vertex operators in some quantum algebras, which might be like new algebras. I don't know, but I wasn't able to find such expressions. At least not now. Just some two complicated sums. It's not clear how to express them as some residues. Or maybe I just bad at it, I don't know. However, in the end, I will give a brief comment about the relation to Andrei, to Morozov-Mironov Zinkevich work, where they actually find some relation of the Hamiltonians to quantum toroidal algebras, but they haven't used any of this. It all wasn't necessary. They just match the eigenvalues.
Okay, thank you. So please continue.
Yeah, okay. Just I don't know. There's not such much questions, so I'm very afraid it's all very confusing. I mean that I give too much information on slides and people couldn't follow so fast. So I'm worrying.
Sorry, I wanted to ask: are there any commutational relations between these Qs and Q stars?
Yes. Well, maybe they're not very beautiful, but I have found them trying to prove the commutativity of this first few Hamiltonians by hand. It was very hard for me, but Andrei Grekov did it using computer. So he just checked. I wanted to check that all my hypotheses are correct, and Andrei Grekov checked it on computer. Yeah, I could write them down if you want. I have, but I need to stop them slides and write down the expressions for Q if you need it right now.
Maybe later, but just to know, are they as ugly as these formulas are or not?
No, there are some quadratic commutation relations. The commutator of these two Q's will be expressed as quadratic relation in Q's.
Thank you.
Yeah, okay, I'll show you in the end. Actually, they are written in the end, in the very appendix, very last appendix of this paper. Just also I add them, but they wasn't needed actually. So okay, now the next and almost last part of the talk is just to explain how to arrive at this expression. I hope it will be, well, it's probably the hardest part of the talk. So I'll give only a sketch of the proof because the proof itself is quite, yeah, it's very technical. So the idea is to express the Hamiltonians not in terms of Cherednik operators, but in terms of so-called covariant Cherednik operators. They do not commute even for Rusinars already. I don't. This expression actually might remind you the role of Lex operator for Rusinars system, and UI is just some already completely auxiliary operator. However, both of them are covariant with respect to the action of Sn symmetric group on coordinates. So if we try to exchange, for example, y coordinates with j coordinates, zy will be mapped to zj. The same for u. And this will be very helpful because then we will be able to express everything in terms of z1, u1, and permutations. And then we'll need to take limit of this only z1 and u1. Here, the first non-trivial statement is like analog of the Cherednik theorem, but for these covariant Cherednik operators. That our Hamiltonian IN could be expressed in terms of them. Also, in such form, we take some non-trivial expressions and then restrict on space of symmetric functions. For this expression, I also have like a sketch of the proof, but not on slides. I could do it on Zoom Blackboard if someone asked in the end. The same as for covariant Cherednik operators or non-covariant Cherednik operators. The proofs are similar, and this proof actually uses the Cherednik theorem. That's why I told you that Cherednik operators are necessary to take the n to infinity limit, because they're actually used in proving this statement. But I decided to just skip the proof at first reading, so to say, because otherwise we will get stuck.
I'm sorry, yeah. How are these covariant operators connected with ordinary?
Yeah, okay, nice question. In principle, there's no direct connection, but there is some lemma. Okay, let me then stop sharing this screen and share the Blackboard thing. Oh, okay, so the relations which will be needed and which was proven in Nazarov Sklyanin paper is the following. So if lambda n1 is space of polynomials symmetric in x2, xn. This is one which we mentioned in Pasha's question. then Z1 restricted to lambda n1 will be equal to C1 restricted to lambda n1. So this is a statement which is needed for all the proofs all the time. The rest is done by induction and by permutation. We only need this.
Statement about only the first one, the first operator, right?
Yes, right. So you might try to get the analogies for different operators using some permutations, but as you need to take into account that CIs are not covariant and so on. So it's easier, always easier to use the first one. It was proven for the first one, and the rest one not needed because actually proceed by induction. Just really, some sense using this thing, we could get back to the case when we have x2, xn variables and then use induction. That's the idea of all those proofs, right? So, and the relation only used like that.
Thank you.
Okay, so now let's move on better to the second step, and the proof maybe might be given separately. Sorry. Yes, that's what I was talking about. We express everything only in terms of the first one and some permutations. So now, yeah, with this new operator V1, which actually almost the same as U1, but just with some total permutations. Now, the idea is to express the inverse limit of B1 and Z1, and from them obtain the inverse limit of the whole Hamiltonians. However, Z1 and B1 do not preserve the space of symmetric functions, but they preserve the space lambda n1, which we just introduced in the Romas question, space of functions symmetric in all variables except for x1. So that's how our auxiliary spaces appear. That was asked by Pasha, also in the middle of the talk, that now our Z operator will map lambda, space lambda to space lambda V with new formal variable V. And we will map lambda V to lambda W. And they will commute with the corresponding projections, namely the one which sends V to x1, this variable which is not, which in some sense additional. It's not additional, but it's the one in which they're not symmetric. And tau n, which sends W to t to the power n. Yeah, that probably maybe we finally get to the answer to Pasha's questions. To Pasha's question about what are the natural projections for Z operations and what is the natural projection for this formal V variable.
Yeah, thank you. I wanted to ask, what is I in that formula with some on maybe on the previous slide?
I
is summation index.
Yes, just summation. I mean, what?
No, in the upper formula. Where is I?
Yes, sorry.
Variables.
There's no I. Yeah, there's no I. Yeah, sorry. There's no summation. yeah, sorry. There should be no summation. Summation already inside of V1. Yeah.
Okay.
Yeah. Oh, sorry. Yes, it's a significant mistake. Yeah, sorry. Yes, way too early. So now the next step is to construct the inverse limits for Z1 and V1, which we'll call here Z and V. But here also probably only give the answer. If you know, yeah, so I really feel embarrassed that I always only give the answers, and it takes already huge time just to introduce all of them. So Z is a product of W, big W and gamma, and H W and gamma expressed as some operators acting on lambda V, right? Also as a product of two operators. One just shifts of V they do not act anyhow on coefficients, which are symmetric functions. They only shifts v by q inverse and t. And the rest, again, our favorite whole little wood polynomials, q, qv, and q star v. The only difference here is instead of v, for w, we actually have v inverse, but more in some sense, such v inverse, which for all powers of vn acts as v inverse, but for 0 it just sends, but for 1 it just sends to 0. So in such a way that the actual inverse of v never appeared. It just kills identity. The natural way to think about is this operation v square or v circle is operator conjugated to multiplication by v with respect to standard scalar product on space C of v. Yeah, where vi is orthogonal to vj as soon as I not equal to j. Just yeah, conjugation to multiplication. So that's the answer. And from the answer for z and v, we could get the answer for, no, I forgot about vn. Yeah, sorry. We have z and gamma, and also vn, v, which, as I promised, will send lambda v to lambda w. It kills all the powers, but creates the power of w in such a way that I even decided to mention how to take square power of it, because it's not so easy. Here it's not, here a bit breaks our standard convention. We also raise w to the power n, because w will be turned into t. Like I decided to put it here instead of trying to introduce different projections. I think it would be more natural to change the definition of square power for this operator v. Yeah, and as soon as we have z, w, gamma, and v, we could use the formula above, the one with the mistake, which Pasha corrected, to get the expression for the inverse limit of the Hamiltonians. Just it looks like that. And the last step is to, as you remember, divide by the variable w, by theta function of w, to get the expression which will not depend on w. Yeah, this curly e. And I'll explain in the next section how to do it. As you can see, the only place where w appears is inside of v in one of only in one power. Oh wait, it's also a mistake here. I changed. I wanted to fix the mistake and I fixed it in the wrong place. Yeah, so v to the power m is sent to minus qm when m is bigger than 0, and sent to w to the power n when m is equal to 0. Yeah, sorry. So vm for all powers of v, it just gives us whole little root function, and for 0 powers it gives a new variable. Yeah. So here instead of n it should be m, and here it should be n. Yeah, I just inaccurately changed. I wanted to fix this mistake, which I corrected in the wrong place. Yeah, sorry, they haven't noticed it. So because of that, it's natural for us to decompose the space lambda v into two spaces, lambda and v times lambda v, because we know that the variable w appears only in one place. And if we decompose everything with respect to this decomposition, express our operators in terms of 2x2 matrices with respect to this decomposition, we will be able to factor out the w dependence, because it only enters like that. Here, how this alpha, beta, x, and y variables operators are introduced, which I mentioned inside the answer. Yeah, but I also will not probably give in slides the the derivation, you need to substitute them here, these 2 by 2 matrices, right? Express E of U in terms of these matrices. And that's how this 2 by 2 matrix appeared, which Kolya was asking about. And then dependence of W will actually be factored, and you would be able to divide by theta function of U W as expected. And arrive at this ugly expression with inverse, with the determinant. Yeah, the inverse appear because we have inverse of P that UZ here. Well, this inverse gives rise to the inverse of this 2 by 2 matrix, which Kolya mentioned. That's how this determinant appeared. Okay, so that's more or less all explanations. I actually wasn't keeping track of the time. I don't know how long it takes. I think it takes a long time. So now we are left only with either giving some explanations of the proof which I didn't, which I skipped in the main body of the talk, or we could go to the relation to elliptic quantum toroidal algebra, which was derived by Mironov, Morozov, and Zinkevich. Yeah.
Well, I think we should now probably stop here for questions. So
yeah, okay. So it's kind of long.
If there are still questions, and what kind of questions, and then so please questions.
Yeah.
I'm sorry, Andrei. I did not understand. Why do you invert the matrix? Right. Could you please show the formula to which you like substitute?
Yeah, right. This formula E of U. Here we have inverse of P theta UC. So what you need to do is the following. We have W gamma here, right? As you remember, Z was a product. Okay, maybe not remember. W times gamma. So what we need to do, we just take these matrices, W gamma, multiply them. Then we take P theta function. There'd be some ugly sum, and then we need to invert it. But it's still with 2 by 2 matrices, but just with interest equal to the P theta functions. We need to invert this 2 by 2 matrix, and we'll get some kind of determinant like that.
Great, thank you.
And how did the function of matrix appear the first time?
How it appeared?
Yeah, how did the function of 2 by 2 matrix appeared?
Yeah, like that. Out of this W and gamma, we compose Z and substituted here. Here it appeared like, yeah, here we have the inverse. And this one appeared from the theorem the proof of which I skipped. Yeah, from covariant Cherednik theorem, so to say. It was the inverse already there.
Could you show the slide?
Yeah, this one.
And where is the matrix here?
But here it's not a matrix yet. I mean, here we have some Zi are still operators, right? Okay, let me try to explain. So in this formula, Zy's are just some operators, like what is written on above, right? Some complicated. Yes. Then we could rewrite them with this formula, which has mistaken it, only in terms of Z1 and V1. Yes, there should be no sum here. Then for Z1, V1, and gamma 1, we construct inverse limits, which will be operators mapping lambda to lambda V and lambda V to lambda W. Yes, for which I'll have given the explicit expressions. So now actually the Z are now some operators acting on infinite dimensional space, which are graded by powers of V. It's like lambda plus V lambda plus V square lambda and so on. It's some infinite dimensional matrix actually, right? Right now Z, here's an infinite dimensional matrix. But now we decided to decompose, like in some sense, emphasize the importance of lambda, the first term in this sum in sum of lambda v, decompose it like in the following way: lambda plus v times lambda v. And we could always write down, in some sense, each the first block here, right, is just really one by one matrix. But other blocks here is actually infinite times infinite matrix, v times lambda v. Yeah, maybe it wasn't clear, right? But alpha, beta,
Yes,
x,
yes,
y
it's clear.
are still operators acting on some infinite dimensional space v lambda v. So it's not actually 2 by 2 matrix. It's still infinite time infinite matrix. We just write this matrix in a block form. We just
It's clear, Andrei.
yeah. Okay. Sorry.
Okay.
And this is why in this last formula you have terms like theta of u, which is like 1 by 1, and theta of y or theta of x, which are infinite by infinite. Yes. Or,
yes, right. Theta of u appeared like because from here, from this multiplication, which was first term, which was 1, which is just gave us 1 identity here. And it was after taking, yeah, if you take b theta function of just identity operator, it will give you just theta function.
okay.
Actually, I'm very curious. Maybe there is some beautiful geometric meaning of this operation. I don't know. Something have to do with equivariant k-theory. I don't know. Some sort of sum of infinite number of equivariant k-theories, but I haven't explored it at all. Yeah, I'm kind of.
So the rest, no more questions up to now.
I also wanted to ask. I was confused about the discussion. So, do you obtain some integrable system like some commuting operator with this UI? IU, I mean.
IU, yeah, okay. So the status of this statement is the following: if Shakirov-Koroteev Hamiltonians commute, then it's a theorem that this will also commute. So it's a theorem mod Shakirov-Koroteev conjecture. Yeah, it's like that.
So it's like you took the first Koroteev Hamiltonian and worked with it?
No, not the first, all of them.
The generating function.
Yeah, we take the generating function.
But in a limit, yeah, when one of the parameters like p disappears.
Yes, exactly right. So it's also maybe a nice question. Could it be generalized to the case when p is not equal to 0? And for example, the Cherednik construction that I mentioned in the beginning actually could be, and Andrei Grekov did it in 2 by 2 case, but it just gets technically very complicated. Still, you could define some elliptic air matrices and also get some like double elliptic Cherednik operators and still get the same statement even for true Dell system. The second part, n to infinity limit, I don't know because it's more technical. Here I just take the almost already solved Nazarov Sklyanin case. I mean, solved Nazarov Sklyanin case for McDonald's, and it was a huge luck for me that these operators actually also act on symmetric functions naturally. So all the machinery of symmetric functions worked. I just use it. If I would like to do it for Dell, I need some sort of elliptic symmetric functions, and the inverse limit will not be just one Fock space. It will be some like doubled Fock space, and I'm not sure that it will work, but probably it could be done also for double elliptic case.
Well, you did a discussion that like Andrei Zotov checked that some operators do not commute. So these operators IU, like if you check numerically, they do commute.
Yes, right. That's also very tough calculation. That's why I decided to do this expansion, right? I would like to check that I0 commute to I1 to the first order. So I need to calculate commutator I0 with I1 and see that it's 0 to the first order. And it actually all boils to proving the commutation between, I think, G0 and K0. This Andrei Zotov checked on computer for some first powers. Yeah, but in some sense, the commutativity of these Hamiltonians follows from the commutativity of Shamil's and Petr Koroteev's Hamiltonians. So I was in some sense already calm because the construction is actually rigorous. And because Shamil checked his Hamiltonians like to very high orders that they commute. So there should be no problem with n to infinity limit case.
But is it correct that you can prove that these Hamiltonians have common eigenfunctions or not?
But I think if I would be able to prove that, that'll be it. I mean, okay, they need to be orthogonal, right? But that will be already proved. Now I only know that they have some eigenvalues, and a conjecture that we know how this wave functions look like. It's actually given, they already known explicitly to all orders, but it just, I think there's no direct proof by calculation. It's just too complicated, I think, and there is no no explicit orthogonality between them. The orthogonality relation between them, as you remember from Shamil's talk, also was a conjecture. It was done for 2x2 case, but it's not clear how to generalize it. However, I think I might comment a bit on the commutativity of this n to infinity Hamiltonians using the results of Morozov, Mironov, and Zinkevich, because as soon as you relate them to the commuting sum algebra of quantum toroidal algebra, if you do it rigorously, that's a proof that they commute. Yeah, sometimes it's like, I don't know, I couldn't, because it's not my paper, I couldn't, I don't know, say that they prove something because I don't know exactly. But if it's everything done rigorously in the paper, it will be proof because they match the eigenvalues. And I think if eigenvalues match, then the operators are conjugated. And these conjugated operators, which they found, they are the center of, I mean, not center, it's a commutative subalgebra of elliptic quantum toroidal. So I think it should be a proof of commutativity. But I'm not sure. I don't know. You might ask.
And is it possible to do something in classical case? Something more like prove something?
Commutativity.
Yeah, yeah.
No, as I mentioned in the beginning, yeah, it's like a question of, it's like a, it will be like part of, it could be separate, part of separate talk, right? I only mentioned the result there. What could be done is the following. We can find some sort of Monakov L operator whose determinant generates this, generates the Hamiltonians. However, this even Monakov triple will not give you the proof of commutativity, and even the Monakov triple we actually do not prove. We do not prove that Monakov triple is equivalent to equations of motion. Monakov triple equations are equivalent to equations of motion. We just did it one way, so it's all not finished there, and there is no hermetic structure. We couldn't also find it. As you know, hermetic structure, classical hermetic structure is needed to prove the commutativity usually, yeah? This error relation is used to prove the commutativity in classical case, and we haven't found it. So I guess no, classically we haven't also succeeded with the proof.
I also wanted to ask, so in Koroteev case, we can take this n to infinity limit and then take a kind of classical, quasi-classical limit from there, and this way we get a kind of Benjamin-Ono system. Is it possible to do something similar here?
Take the classical limit already after infinity limit.
Yes.
No, well, okay. So you mean the variables Pn and Pn orthogonal, which is P minus n, in some sense, become commutative. Become canonical conjugated with respect to some symplectic bracket, right?
Yes.
Well, I don't know. In principle, it is possible, right? It's just straightforward limit, but I don't know what the expression to expect. As you can see, it's all non-local. Yeah, and I couldn't even write down the next term so easily. It was non-local already before, even for Rusinars, because it's expressed in terms of Q, not just P. And Q, we have some infinite number of Pns already inside of G0. And for currently I0, it gets even worse, right?
Oh, yes, I see. So maybe I had asked even before about resonance. Yes.
It's a very interesting question, because Rusinars corresponds to intermediate long wave equation in this respect. And what should we put instead of intermediate long wave equation in double elliptic case is unknown.
Yeah, this construction generalized, as I understand, like the trigonometric Benjamin-Ono and trigonometric integrable long wave to elliptic and momentum dependence. Yeah, I think let's find the answers. Igor Moisey's question at the beginning. Well, I just forgot how it's called. I forgot how the system is called.
Thank you.
Well, so if there are no more questions, let's thanks Andrei.
We could go to
another Andrei, and maybe maybe we'll come back to this issue once more. But now I think many people are already killed by your, as you said, ugly expressions, which, well, maybe not ugly, but well, maybe you say, just repeat very briefly. So you said that you wanted to find some meaning of these expressions in terms of representation theory of some algebras, yeah?
Yeah, right. Okay, let me.
As I understand, you said that you have not found it.
I haven't, but Mironov, Morozov, and Zenkevich found in the way I could explain right now. I will explain briefly. So they do it like that. We have elliptic quantum toroidal algebra, which could be expressed in terms of Greenfield currents, x plus minus of z and psi plus minus of z. This psi plus or psi minus, they form a commutative family. So psi plus of z commute with psi plus of w. And there is some representations of this elliptic quantum toroidal algebra, and there is at least one, which is exactly Fock representation. So it has at least one Fock representation, which is like usual Fock. One boson, just one boson. Wait, sorry. Okay. And which has the basis numbered by one Young diagram. They call it E lambda Q T omega. And they identified the action of horizontal generators E and M on this E lambda as usual bosons, usual power modes like P1, P2, P3, and so on. However, at the same time, as there's just one Fock representation, the generators Psi, which are vertical, actually, vertical generators, are also described in terms of these bosons somehow. And at the same time, they from the construction representation, we know how they act on this basis. They're diagonal in them. So they just found that Psi plus of Z act on D lambda with the same eigenvalue as we found. Actually, the ratios of these eigenvalues, some theta functions.
Z
So
is U, right?
yeah, you may think it's U, right? It will some Q, lambda, E, T, 1 minus E, U, sorry, U already appeared. And something the same shifted by Q here. So as they act on the same Fock space and have the same eigenvalues, this means probably they're conjugated to each other. And this means automatically, if this commute, those should also commute. And what I did is just explicitly expressed this Psi generators in terms of this single boson, which comes from X plus, actually, this representation. But it wasn't needed for their result. And they even give the explicit relation. I think Psi plus of U is something like curly E U divided by curly E Q U conjugated by Schur automorphism and conjugated with respect to Schur scalar product. It's like that. So Pn sense -1 +1 Pn and conjugation. I denoted actually. I denoted differently. I denoted like that. Yeah. So by the eigenvalues matching, it should be the same Hamiltonians, and they actually even checked that the eigenfunctions are the same. They found this dual basis to E lambda to be dual basis to E lambda times this automorphism, Schur automorphism omega to be this eigenfunctions which Shamil found explicitly. That's the one which was mentioned, and the one about which Andrei Grekov asked me how they look like. They found that they are actually dual basis to this E lambda. So they give like some insight of quantum version of this PQ duality for this elliptic case, because E lambda actually satisfy some kind of elliptic Piri rules, which exactly reproduce the expression for elliptic Resonance Hamiltonians, right? As you remember, if you remember how Piri rules look similar. But in principle, this should be explained better by Igor, right? Just Pasha told me that he's not like planning immediately to invite Igor, so I decided to include this like in the end, a brief comment.
Yeah, but it's better to. Okay. So thank you. Спасибо, Андрей.
Okay.
Thank you.
И да, и другому Андрею тоже спасибо.
Спасибо.
Ладно. Ну что, все, Паш, да? Вы останавливаете? Или вы уже остановили?
Спасибо всем.
Okay, thank you for inviting me. Thanks the organizers.
Спасибо.
Спасибо.
Спасибо.